Well, good afternoon, everyone, or good evening, good morning, depending on where you are on the Earth. And welcome to this session about things that go bang in the sky. As mentioned, I'm Karouzos. I'm from Nature Astronomy. And as part of the Spring of Nature, our mission is to really open doors to discovery. We are addressing the challenges that are set out by the United Nations Sustainable Development Goals by finding ways to connect research to everyone who really has a stake in improving the world and getting the next decade right. Astronomy in particular is kind of unique in its ability to connect our everyday experience with something that is really much grander than what we are. Astronomy inspires people to think big. It's an excellent gateway to fundamental science, and also really it connects everyone under one common sky. With observatories in some of the most remote corners of the Earth, astronomy helps spur development, leads educational efforts, and helps reduce inequalities. Yet, unfortunately, a lot of work still needs to be done. Astronomy, like most fields of science, is suffering from inequality and exclusion. Racism, sexism, and many other of these isms are still a big problem. So I wanted to mention that today, the 10th of June, has been marked as a day to shut down academia and shut down STEM and strike for Black lives. These initiatives call everyone in academia to action in the wake of the senseless loss of Black lives in the USA and elsewhere. Nature and the Nature research journals are today participating in the strike for Black lives by delaying publication for 24 hours as a show of support for these initiatives. We, as editors, join the research community to reflect on systemic racism and the personal and collective actions that we need to do to address it. Together with the rest of the research community, we must listen, we must reflect and learn and act to end systemic racism. I also wanted to state here that the speakers of this session all fully support the movement, but have agreed to fulfill their commitment to the CogX and also to you, the participants. Well, moving on, we have a very interesting session ahead of us, so let me get right to it. Today's discussion is about the transient sky, as you heard. And by transient, we mean something that happens very quickly and it's fleeting. However, some of these phenomena are really so energetic that they can be observed all the way to the edge of the known universe. Some examples include the explosion of massive stars, like supernovae, the collision of stars, and also phenomena that surround black holes. While the knowledge of the changing universe has been around for quite a while, technology, and in particular artificial intelligence and machine learning, has only recently allowed astronomers to efficiently monitor the night sky, identify these transient phenomena promptly, and then go ahead to characterize them and understand what is their nature. To discuss this, it is my pleasure and honor to welcome our three panelists, all experts in transient astronomy. I would like to introduce all three of them, and then we can move on to the first talk. So first, let me welcome Marika Branchezi. Marika is an assistant professor at the Gran Sasso Science Institute in Italy and is the current president of the Scientific Council of INAF, the Italian National Institute for Astrophysics. She was recently chosen as one of 10 people to watch in science by Nature and was also named one of the 100 most influential people by Time magazine. In 2016, she was a co-recipient of the Breakthrough Prize in Fundamental Physics for her participation in the discovery of gravitational waves. Also with us, we have ya-eer Arcavi. Ya-eer is an assistant professor at Tel Aviv University in Israel. He has been the recipient of many prestigious awards and fellowships, among which I would just mention the Nathan Rosen Prize of the Israel Physical Society and the NASA Einstein Postdoctoral Fellowship. In addition to his extensive scientific contribution, ya-eer is very active in outreach within Israel and internationally. Finally, let me welcome Vikram Ravi. Vikram is an assistant professor at CogX in the US. He's the co-principal investigator of the $5.3 million Deep Synoptic Array that is looking to detect fast radio bursts, and you will hear more about that in a bit later. And for his work, Vikram has been awarded a number of prestigious awards and fellowships, including a Kavli Fellowship, the Charlene Heisler Thesis Prize, and the Clay Postdoctoral Fellowship. Welcome all. Our panel today will start with 3 short keynote presentations by our panelists, each focusing on a different aspect of transient astronomy, and then we will have a moderated discussion between the 4 of us. The discussion will be followed by a short break, and then we will reconvene and you will have a chance to ask questions to the speakers. I'm sure this will be an exciting session, so without further ado, I would like to invite Marica to start us off. Thank you.
Hi all, I want to start with a new exploration of the universe. So the 14th of September 2015, for the first time, the LIGO antenna in the United States detected gravitational waves. The signal was really very short, fraction of a second, but this very short signal was able to tell us a story that happened in the universe long time ago. We were able, for the first time, to detect the signal from two merging stellar mass black hole. Gravitational waves are ripples in the space-time that propagate at the speed of light. And for the first time, we were able to build instruments able to measure this ripple. So these two black holes merge and form a more massive black hole. And at the moment of the merger, the power emitted was, in gravitational wave, was larger than the power of all the stars in the observable universe. These gravitational waves propagate through the universe and travel across many galaxies, a billion of galaxies, and the 14th of September, it reached our Earth. Gravitational waves is really a new way to observe the universe and to see what before was invisible. Today we know more about black hole. We know that they live in binary system. We know properties about their mass, about they rotate among themselves. We know a bit about the frequency of this merger. And we are starting to understand also how they form and how they evolve in the cosmic history. I am sure that all of you saw recently this picture of a supermassive black hole. This is not 10 times the sun, but this is billion of times the sun. These are supermassive black holes that are at the center of the galaxies. And this is really a picture at the center of this black hole in the region before the horizon of this black hole. Everything that goes inside the horizon, we are not able to see because nothing can escape. So this is a picture of the material really at the border of this black hole. We don't know really what is the connection between the population of stellar mass black hole and these supermassive black hole that are at the center of the galaxy. And I think that a mystery that we will try to resolve in the next years also with gravitational wave is this one. What is the connection among these two populations of black hole? The 17th of August 2017, we had another outstanding discoveries. So we listened with the two LIGO antenna, but also the antenna that we have in Europe, Virgo. We listened a different signal, longer, almost 1 minute, and then our dream in front of us. 1.7 seconds after the gravitational wave signal, the Fermi satellite observed a flash in the gamma ray, a gamma ray burst that was confirmed by integral. What we were observing was not two black holes, but the dense, the spiral of two neutron stars. Neutron stars are very exotic stars, are two suns within 20 kilometers, extremely dense. A tablespoon of neutron star weight almost 1 billion of tons. And we saw this final merger, this final spiral, and when they are close, the neutron star, due to the tidal forces, they start to be disrupted, and we have the merger, and then a lot of material around that form an accretion disk and two jets of material and energy that propagate at the speed of light. So we have two relativistic jets that gives rise to the gamma ray emission, to the gamma ray burst. But we have also a material that is a bit slower, almost 1/3 of the speed of light. And this material is rich of neutron, is a material in which we expect the formation of heavy elements. And we expect all the color of light from these emissions, so from the ultraviolet to the near infrared. So the signal from the gravitational wave arrived around the lunch time, and we had a problem in the data. You can see here a yellow part was the noise. We worked a lot to remove this noise, and 5 hours later we had a sky localization. This is extremely important because it is where the astronomer with the satellite and telescope has to point. So this signal was closer with respect to the black hole, So the signal traveled to Earth, and it takes about 130 million of years to arrive to us. It's a region of the universe more close to us in which we know the galaxy. So the Chilean telescope started to observe this region that you see here in blue, that is the sky localization. And in this volume of the universe, we know the galaxies, and there were about 50 galaxies to be observed. And in one of these galaxies, we observed a new light that was not there before. This is a kilonova emission, and we observe an object that was with very high temperature at the beginning that decreased a lot its temperature, and from a blue color became red. And these objects show us how heavy elements form in the universe. So with only one event, with only one gravitational wave from a binary system of neutron star and the light, we were able to impact a lot of astrophysical field. We know more now about relativistic jet. We know more about kilonova. We know more about the formation of heavy elements in the universe. That was a big mystery for many, many years. We know more about matter in neutron stars, so matter in extreme condition of density. And using the light and the gravitational wave signal, we also are able to have a new way to study the expansion of the universe. And with this signal, we were able also to study a bit about the origin of neutron stars, so how they form and how they evolve. This was really a collective effort. So this was a discovery that was done by more than 3,000 of scientists, engineers, astronomers, gravitational wave physicists, really women and men. So really was a discovery that showed how much is important to overcome diversity, and how much is important to work together, worldwide scientists. And really, I think that shows us how much it is important to remove walls and to build bridge. And this is something not only for the science, but this is something for the society. And the diversity is a big reach for everyone. And I think that this discovery shows us how much diversity is crucial to overcome the challenges of science.
Thank you very much, Marica. This was very interesting. Indeed, gravitational wave detection was one of the biggest discoveries, not only in astronomy, but physics and science, fundamental science. Thank you very much. So next we'll be hearing from ya-eer Arcavi, who will be linking these gravitational waves to how we detect these objects in other ways.
Yes, thank you very much. It's so great to be here and follow Marica's excellent introduction about gravitational waves. And so what I work on the astronomy side that tries to look for that light that Marica mentioned that comes out from these mergers. So let me tell you a little bit about how we find these fleeting events and how we find the light from them, because it's quite challenging and new to us. So here's another illustration of the neutron star merger that Marica was talking about. You have two neutron stars merging. They send out these gravitational waves into space, and that is what was detected by the gravitational wave detectors for the first time in August a few years ago, 2017. But also, as Marica mentioned, there's all this material flying around, and it produces the heaviest elements that we know. So these elements that are kind of in the these last two rows of the periodic table are created in these neutron star mergers, but also, most famously, gold is created there. And so I want you to take a moment, if you have a piece of gold jewelry on you right now, take a look at it, because the atoms that make up that piece of gold, the only place in the universe we know that can forge gold atoms is the merger of two neutron stars. And so every atom in that piece of gold that you have, if it could tell its story, would tell us that it was born in a merger of two neutron stars sometime somewhere in the universe before making its way to Earth and to your piece of jewelry. And that was a theory until this neutron star merger was discovered, and now we know it as an observational fact. And the reason we know it is because when this gold and all these heavy elements are created, they produce light. And we call this light flare a kilonova. And our challenge was, can we actually see it? So the gravitational wave detectors detected the gravitational waves. That means a neutron star merger just happened. Can we see this flash of light from the creation of the heavy elements, this kilonova? So how do we see distant things in the universe? Well, we use telescopes. And we've gotten pretty good at building telescopes. We make them now, we put them on high mountains, so they're above the clouds and they don't have a lot of atmosphere to look through. We make them very big, and we're planning to make them even bigger. So on the top you see the two Keck telescopes in Hawaii, and in the bottom is a simulation of the extremely large telescope. This is actually its name, the extremely large telescope that's being built in Chile. And so you see some cars there for scale. So we're very good at making telescopes bigger and bigger, which means we can see things that are fainter and further away than ever before in our universe. And we're also good at having many different types of telescopes, sending telescopes into space so we can see radiation that doesn't make it down to the ground. And also telescopes that can see radio waves, which you will hear about after me by Vikram shortly. So we're good at seeing things far away, but still it doesn't help us that we have the very big telescopes and very sophisticated telescopes, because you might notice here in this slide that they are looking in the wrong direction. The neutron star merger is in one place and they are not quite looking at it. And the reason is that when gravitational waves happen, the localization on the sky is not super precise. So here's a typical map of the sky shown kind of in this oval, like we're used to seeing maps of the Earth. And that banana-shaped thing is what we were expecting to be a typical localization of gravitational waves on the sky. And the little square beside it is the typical field of view of most telescopes. And so it is very hard to find a faint flash of light in that huge area, with that tiny footprint, especially since it's very fleeting. In a day or two, it's gone. And so you have to find it very quickly, and so you have to be smart about it. And so one of the ways we were smart about it was that we thought, well, you don't actually have to search that whole area of sky, because stuff in the universe is not just randomly distributed, it's clumped up in galaxies. And we know more or less where galaxies are, at least the ones that are pretty nearby to us. So if we're lucky, the neutron star merger will happen in a galaxy that we know exists, and it'll be in our catalogs, and we'll look there and we'll find it. So that was our strategy, and several other groups as well. I'll also say that there are many groups that do have much larger fields of view, and this is a very new technology now, that telescopes can see huge parts of the sky. And so they can just tile the whole region, and then even if it's in a galaxy we didn't know about before, we'll find it. So here's that localization again from the neutron star in 2017. Here's the actual position of galaxies that were in that position that we searched. You see the full moon there just for scale. So you get a sense of how big a region of the sky this was. This was actually much smaller than we were worried we would get. So that was where we were lucky, very lucky, number one, in that it was a small region. Our luck number two was that in the fifth galaxy that we looked, which is this one, we saw this blue dot. And that blue dot is light coming from the creation of heavy elements from the neutron star merger, the same one that created the gravitational waves detected by Marica and her team at the gravitational wave detector. So this was the first time we saw both gravitational waves and light from the same event. And it's like studying something with two senses now. We were able to answer so many open questions in physics and astronomy just from this one event. And also, more importantly, I think, open up many new questions. So here's what we saw, the brightness of the event. Marika mentioned it started out blue. Everything that's hot in the universe is blue, and then it gets red as it cools down. And so it started out blue, got brighter, and then got fainter and redder very quickly. We actually never seen anything this bright evolve this quickly before. And it was just staggering to watch it almost in real time evolve so fast. But you'll notice another challenge here, which is the time and scale in which it's changing is shorter than a day. You see the days down below in the x-axis. And so if you have your telescope, say in Chile, you can only observe at night, and then you can only come back to it the next night, and you have a gap of the whole day where you can't observe, and you're missing all of these changes. So how were we able to follow something that changes more quickly than we can observe it? Well, here's another new tool in astronomy. It's not just about making telescopes bigger and on higher mountains, it's also about dispersing them around the world. So this is a unique new resource we have in astronomy. It's a global network of telescopes that are completely robotic and can talk to each other and can pass observations from one to the other. And that way, as the Earth rotates, that is how we actually got this data, and we're able to see what this event was doing, because at every given moment, we had a telescope somewhere in the dark that could observe it. So from Chile to Australia to South Africa, we were able to keep tabs on it as it was changing very rapidly. So this is a completely new technique that we now have in astronomy, and we can use it not just for these kinds of things, but for other things that go bang in the night. For example, supernovae, and here on the left is an actual picture of an exploding star, a supernova, and we can use these networks of telescopes to catch these things as they're exploding the first few hours, and that is teaching us a lot of physics that we have no access to in any other way. And just another example, this is an illustration on the right of a star getting torn apart by a supermassive black hole, these million or billion solar mass black holes that Marica mentioned at the beginning of her talk. A new way to study them is by catching very rarely when a star gets torn apart by one of them. And since we have all these telescopes monitoring the sky now so closely, we can start to find very rare events and gain even more access to laws of nature and laws of physics that we had no way of studying before. So I'll just end by saying that the future is really challenging. The next big thing in our field is about to happen. It's this new telescope called the Vera Rubin Observatory, and it will scan the sky from the Chilean mountaintop every night and discover, because it's so big and has such a huge camera, 10 million new astronomical events per night, every night, for 10 years. And so the question everyone in astronomy is now asking themselves is, how are we going to deal with that? There's going to be a deluge of data that we have never had to deal with before, but there's going to be so much interesting science hidden in there that we want to make the most of it. And here is where computer-aided artificial intelligence, machine learning, is going to have to sift through this and tell us, hey, this is interesting, you should pay attention to that, because no person can look at 10 million events per night. And so here's where we're going to need help from expertise in those fields and in managing just these huge amounts of data. So it's going to be challenging, but I think it's going to be fun. Thanks.
Thank you very much, Iair. That was very interesting. And indeed, it's like a technical challenge. Perhaps we haven't faced anything like this before in astronomy in the terms of the amount of data that we'll be receiving. And I think we'll be discussing about this more in the discussion later. Thank you very much. The last talk, introductory talk, will be by Vikram Ravi, and he will be talking a bit about radio astronomy and how it connects to everything we've heard so far, and also a very special and particular kind of events called fast radio bursts. Thank you.
Really glad to be here and be able to tell you a bit about how we can use radio waves to really probe some of the most extreme and energetic phenomena in the universe, as well as push our boundaries of our knowledge about physics as well. One of the most amazing things about the universe is that we find phenomena that are completely unimaginable here on Earth, that we cannot even conceive of putting together in labs. But we can actually say something about this by using our observations of the night sky. So one of the really compelling things about astronomy, I think, one of the things that really makes me really love my job is our opportunity to see pictures such as these. So we're all familiar with the night sky as it's revealed to us in optical light. On the right here, we see a picture of a large galaxy cluster, a grouping of galaxies roughly 3 million light years across. Over here, we see a region where baby stars are being born, a star-forming region within our own Milky Way. And finally, we see an image of the core of the giant elliptical galaxy M87. This galaxy is about 50 million light years away. And this jet of material is in fact being expelled by a giant black hole at the center of this galaxy. Now, what would this look like if you could see with radio eyes? Well, this. What we now have here is gas that has been accelerated to speeds extremely close to the speed of light, spiraling around dense intergalactic magnetic fields, revealing this amazing filamentary structure within this galaxy cluster. All these points are real. Over here, we in fact see not just a baby star, but actually baby planets in the process of being born. This disk is about the size of the solar system, but is less than 1 million years old. And the gaps in the disk have been excavated by planets in the process of formation. Finally, 100,000 times further away, but actually on the same physical scale. So the disk of baby planets is about the same size as this disk of material spiraling around this 6.5 billion solar mass black hole in M87. You saw this image before, and it was taken with the Event Horizon Telescope. To give you an idea of the amazing angular resolution that this image had to achieve to make this possible, the total extent of this disk is about the same size as an orange would appear on the moon. We really are able to resolve such tiny features. And this was demonstrated, I think, with amazing fidelity with observations of this gravitational wave event, where the neutron star merger expelled this jet of relativistic material, where in radio waves over here on the right, you see an image of the head of the jet impacting the surrounding gas, which about 150 days later had actually moved across the sky. We can actually see objects moving in almost real time at distances of several 100 million light years away. This is truly amazing to me that we can actually see real dynamic movement on human timescales, and yet on astronomical scales. And so radio astronomy has a really long history of delivering major breakthroughs in our understanding of the universe. Radio telescopes, such as the Parkes radio telescope over here in the center, a large single dish, as well as arrays of dishes, such as the Very Large Array in New Mexico in the US, as well as the Atacama Large Millimeter Array, or ALMA, in Chile, are able to deliver observations of things such as quasars, shining supermassive black holes that have been known for decades, which revealed our first indication of supermassive black holes at extragalactic distances, as well as pulsars, which were the first evidence for rapidly rotating neutron stars, which, as Marica and ya-eer mentioned, are the remnants of giant stellar supernovae. And now, for the last decade or so, astronomers have been incredibly interested in these fast radio bursts, or FRBs, which are really bright flashes of radio waves that last just milliseconds, but come from well beyond the Milky Way. For the last decade or so, we have not known what makes fast radio bursts, and we also see in their radiation indications of vast reservoirs of matter through which they propagate over their intergalactic distances. And so my group at Caltech, which we started off when I was a postdoctoral fellow a few years ago, and now as faculty, has been building instruments in order to pinpoint the origins of fast radio bursts. We put together a prototype array of dishes about 4 years ago now, which was able to observe a field of view in the sky that was roughly this big in relation to the Milky Way, about 7 by 7 degrees across. You can see here the kind of hands-on work that is required to get such arrays built. And the real challenge here is to try and pinpoint the exact galaxy from which the fast radio burst originated, in order to be able to say something about its origins, as well as the amount of space through which it's propagated. And to give you a sense of the scale of the problem, this is a deep image of the sky in just 1/100th the size of our field of view, taken with the Keck telescopes in Mauna Kea. And you can see that there are still several galaxies that we need to try and sort through to understand the origins. And yet, with the aid of really powerful autonomous data analysis engines, we were able to do this and find a fast radio burst from exactly this galaxy at a distance of about 8 billion light years away. What this told us is that this galaxy, despite being so far away and appearing so unremarkable and faint in this vista of the sky, actually is very similar to the Milky Way, which tells us that fast radio bursts can originate even from galaxies like the Milky Way. There is nothing particularly special about the host galaxies of fast radio bursts. Following on from this, we also put together an experiment to search for the nearest and brightest fast radio bursts, because if we're able to pinpoint their origins in the nearby universe, perhaps even within the Milky Way, we'll be able to say something very concrete about the exact source of the radio waves. And so what we did is we took the receivers that you see at the focus of these dishes and basically just turned them upside down, pointed them at the sky. And because we now have a much smaller antenna, we now have a much larger field of view of the sky. And so we put the 3 stations across the southwestern United States. And on April 28th of just this year, we actually detected an extremely bright radio burst from within the Milky Way, the brightest radio burst that has ever been detected. It was seen, as you can see here in this discovery plot, at all 3 stations. And what this showed was that we were able, with the aid of other telescopes, including the CHIME and FAST radio telescopes, as well as a constellation of X-ray satellites, we were able to trace this burst back to a very special kind of neutron star known as a magnetar. Magnetars are the most magnetized neutron stars, and on occasion put out these bursts of radiation and plasma, one of which appears to have made this fast radio burst-like emission. Although this is unlike anything we've yet detected from within the Milky Way, as you can see here on this plot of duration versus luminosity, it is most similar to the fast radio bursts that we detect at extragalactic distances. And so we now believe that we have a viable way of making fast radio bursts at extragalactic distances. We just need to invoke magnetars, much like those we observe in the Milky Way. And so to finish, I'd like to just leave with a couple of messages. The first is that our discoveries were really enabled by combining these proven, low-cost hardware platforms with almost entirely autonomous data analysis engines. We could never hope to drink from this fire hose of data that our arrays are producing today. And yet, we were able to make the discoveries in extremely rapid amounts of time. The other thing I'd like to really emphasize here is that this paradigm is being adopted by astronomers worldwide. The 2020s will really be a decade of transformational astronomical surveys. Our knowledge of the night sky will be taken to levels that we could never have even imagined just 10 years ago. 1 in 10 galaxies in the observable universe will be catalogued in the next decade. That's a truly remarkable thing to think about. What this means is that access to the sky will be truly democratized. Anyone, anywhere in the world with a good internet connection and access to a computer will be able to access the latest astronomical data and make their own discoveries. I think this is a really great thing to involve a much larger and more diverse base of astronomers in the field. And this is something that we really hope to work towards in the coming years as a field. But I also think that we need to rethink the very nature of discovery. Discoveries in astronomy have traditionally, and I think in many people's eyes, been made by a few astronomers sitting in very large telescopes, sort of toiling away to take deep images of the sky. That paradigm is completely changing. And so, as you've seen in the previous talks, and as I hope I have covered in mine, we really need to rethink the nature of discovery. Thank you.
Thank you, Vikram. That was very interesting, and it's very fascinating, I guess, to see that there are still events that are happening in the sky that we don't really know what they are, and we still have to discover more of them. So now we'll have a bit of time to have a discussion with all the three speakers about what they've discussed. I think the first point I wanted to bring up, and it's something that, of course, all of you touched upon, is the dynamic versus static universe. The idea that the universe changes quite a lot, and we're now able to see this happening. What do you think was that kind of the transition between these two ideas from a very static universe to something that is completely changing the whole time? Any one of you?
I think one of the catalyzers of this was actually technological. It was the invention of these very wide field cameras that are very sensitive and that we can put on telescopes and see large patches of sky at a time. And then suddenly this opens up, whether on a telescope that takes images or telescopes like the ones we just heard, radio telescopes that can see large patches of sky. I think this is key, especially if you're looking for rare things. This suddenly opened up the ability to find things that are super rare and that we were completely oblivious of and blind to before. And so this was completely driven by technology, but then hand in hand, we also needed some technology to deal with all this new data. And so the development of machine learning and strong computing algorithms and the internet, which allows us to do all of this remotely, really came together, I think, to open up like this window in the last few years.
Yeah, it's truly fascinating to think that for millennia we really observed changes in the night sky, like guest stars observed the supernovae, even some eclipsing binaries were known about 2,000 years ago. But I think to add to what ya-eer said, the idea that we can now even just store more and more amounts of data and then go back over them and search in these archives for events, I think that is something that's really driven some of these discoveries as well. Like fast radio bursts themselves were only discovered in 2007 and data taken in 2001. It took us 6 years to go back and just think to look for something that we hadn't expected.
And I think that to all of this, we can add the gravitational wave. It's really a new way to see the transient. So these events that happen very, very quickly in the sky and we can detect. So really, I think that 10 years ago, this was impossible from the astronomical side and also from now also with the gravitational wave. So it's really something that changed very, very recently.
Yeah, and I think I wanted to add that astronomy is kind of unique in the sense that, the facilities, the telescopes are kind of distributed around the world, obviously, and almost everyone has access to all the data that is out there, as opposed to having one lab with one set of equipment that you're doing your experiment. So this, of course, facilitates the discovery in a whole different way than perhaps other fields of science. I wanted to go back to one of the comments that I think Vikram made about AI and the new nature of discovery. Obviously, AI and machine learning is very important to all of your work. I would like to maybe get a few comments about how you think machine learning is revolutionizing the way that you do work now. Marica, if you want to start.
Okay, so I think that is extremely important to overcome the challenges. So, for example, as ya-eer said before, when you have a lot of transient in the sky, you need to find the counterpart of the gravitational waves. You really need something that works very quickly and remove all the contaminants. So I think that to overcome challenges, artificial intelligence is something extremely important. But at the end, I think that so the human being has to work also to understand the data and everything. So for me, something that allow you to overcome the technological challenges, but the creativity driven by curiosity of human beings is still something that has to be in front of artificial intelligence. So I think it's a way to reach the goal for human being in discoveries.
Yeah, absolutely. I think that's exactly it. That we need to use it as a tool rather than to allow it to completely drive the way that we do the science. But at the same time, I think there's another really nice example that's come up in the last little while with the application of AI in astronomy is exactly in that image of the giant black hole, M87, that Marica showed, and I showed as well, where to make images like that, it's kind of difficult for a single person to go through the data and try and infer the existence of this image from this really complex data set. And so it really did require a very, I guess, principled application of AI to extract the highest fidelity image from these data. That image would not have been entirely possible without that application of AI to really make sure that there weren't a million other images that could possibly be consistent with the data as well.
Yeah, and I'll just add that I think astronomy not just uses AI, but also we have new types of challenges that we need to solve, and that drives creativity to develop new methods. So just here at our University of Tel Aviv, we have students that developed a new algorithm of machine learning to solve a certain astronomy problem, but this can be used in general for many other things. And I think this is one of the great things about astronomy and curiosity-driven research in general. It always gives back some application back to society, even though it's never possible to predict what that's going to be and when it's going to happen.
Thank you very much. I think we're almost running out of time. Thank you for all your talks, and we will be reconvening back again for questions and perhaps continue our discussion. And thank you to our audience for being here, and we will see you very shortly.
Want access to more CogX videos? Subscribe now for free at cogx.co.